So due to the d electron starts pairing from here. Up to manganese, the d electrons are singly occupied in the d subshell, but after manganese, from iron onwards, the d orbital, they start. Actually, whenever degenerate orbitals are present, you have to fill with one electron each. As per Hund's rule, then the next electron pairs. So paired d electron do not participate in bonding. Do not participate in bonding. Outermost two s electrons are already there. If these two s electrons participate, iron shows +2, like ferrous chloride, +2. Ferrous sulfate, +2. Ferrous oxide, +2. So iron shows some oxidation states, some compounds in which it is in +2 state. Now the next one, iron can also show +3 in ferric chloride. Ferric sulfate, ferric oxide, so predominantly iron shows two oxidation states. These are all ferrous compounds. It predominantly shows +3 in ferric compounds. You have studied K4FeCN6, potassium ferrocyanide, in which iron is in +2. You have also studied K3FeCN6, potassium ferricyanide, ferricyanide. What are the two IUPAC names? Because immediately we are going to study the coordination compounds also. Whenever there is a complex, you have to know its IUPAC name. The first one, hexacyano or hexacyanido. Potassium hexacyanido. You have to start with the potassium. Potassium hexacyanido. Ferrate 2. What is the IUPAC name? Potassium hexacyanido. Ferrate within brackets Roman number 2. This is potassium hexacyano or cyanido, ferrate 3. These are IUPAC names. But iron also shows a zero oxidation state in its metal carbonyls. This is iron carbonyl, where iron is 0. Or perhaps in all metal carbonyls, metals are in zero oxidation state. like nickel carbonyl, NiCO 4 times. Nickel is in 0. Or you can write chromium carbonyl. Chromium is 0. So what is the generalized statement? In metal carbonyls, metal is always in 0 oxidation state. In metal carbonyls, metal is in 0 oxidation state. Now, iron shows +1 oxidation state, in which complex? We already discussed this point. Iron shows +1 oxidation state in brown ring complex. In brown ring complex, FeH2O 5 times, NO SO4. It is penta-aqua, if you want to name it in IUPAC. Common name is brown ring complex. IUPAC name penta-aqua. Nitroso, iron 1, sulfate. This is penta-aqua. This is NO. NO is not a neutral molecule here. It is NO plus, nitrosonium ion. That's why the word nitroso. So if you take the iron oxidation state as X plus 5 into 0 for 5 water molecules. Water molecule is having net charge 0. +1 for nitrosonium ion. And -2 for sulfate ion is equal to 0. Sum of the oxidation numbers of a neutral molecule must be equated to 0. From this you will get a value of X plus 1. So this is iron's oxidation number +1 in brown ring complex, which again you study in the qualitative analysis. For detecting nitrates, we perform a test called brown ring test. So brown ring test is meant for what? For the identification or detection of nitrates. Now, iron also shows a fractional oxidation state in a mixed oxide. The mixed oxide Fe3O4, which is 2Fe, not 2Fe, Fe2O3 plus FeO. It is called ferric oxide. So here iron 3x plus 4 into -2 is equal to 0. So x is equal to plus 8/3. So iron shows a fractional oxidation state in a mixed oxide. What is the name of mixed oxide? Ferroso-ferric oxide, which is also called the magnetic oxide of iron, which is also called in the nature magnetite. It has several names. In IUPAC you can call it as ferroso-ferric oxide or magnetite, which is a mixed oxide. So students should understand that iron is exhibiting +2, +3, +1, 0, +8/3. These are the oxidation states shown by iron. Now if you look at after iron, cobalt, (27), 3d7 4s2. It shows +2 if 2 s electrons are involved. It can also show +3, +4, +5, because not more than that, because the d electrons are paired here. So this is 3d7 4s2. If 2 s electrons are involved, what is the oxidation state? +2. If unpaired d electrons are involved, only one d electron +3, 2 d electron, 2 s electrons +4, all the 3 d electrons, 2 s electrons +5. So this is called variable oxidation states. After that, nickel 28, 3d8 4s2. It can show +2, +3, maximum +4 only. After nickel, copper 3d10 4s1, 3d10 4s1. So it shows 2 oxidation states, cuprous and cupric. In cuprous state, its configuration is 3d10. In cupric state, its configuration is 3d9. 3d9 4s0. Now, generally, if you ask which state of copper is more stable, mostly students answer cuprous is more stable, because D10 full-filled orbitals and full-filled configuration always gives stability. But between cuprous and cupric, cupric state is more stable than cuprous state because of greater hydration energy. Cupric ion is more stabilized in the form of salts or in aqueous medium. That's why cuprous ions, Cu plus aqueous disproportionate into cupric and copper. This is what I am telling, disproportionation. +1 to +2. What is this? Oxidation. Increase in oxidation number. What is this? This is reduction, because cuprous to 0 state. Reduction. If same element undergoes both oxidation and reduction, we call it as disproportionation. So why I cited this example here, and this is the very, very most important point given in your NCERT book. So cuprous ion is being disproportionated in aqueous medium. If it is already stable, it won't convert into cupric state. Because it is unstable, in aqueous medium it is changing into cupric state and copper. It is a disproportionation reaction. So though in terms of electronic configuration, cuprous is considered to be stable, but the overall stability depends on how it exists in aqueous medium. So cupric ion with a greater hydration energy, it is more stable than cuprous. Now, after copper, the next element is Zn, zinc, 30 atomic number, 3d10 4s2. It only exhibits +2, no other oxidation states. So zinc only exhibits +2 state due to the participation of these s2 electrons, and there is no other oxidation state for zinc. That's why, all the d block elements we should not call as transition elements. Here we should have a clear-cut demarcation. What is the difference between a d block metal and a transition metal? D block metals are those in which the last electron enters into D sublevel. Yesterday we gave 3D series, 4D series, 5D, 6D. So each series contains 10, 10, 10 elements. So total 4 series, 3D series, 4D series, 5D series, 6D series. 4 into 10, 40 elements. All 40 elements, you can call them as D block elements. Because in all those elements, the last electron enters into n minus n d sublevel. The electron won't enter into the outermost, but the d orbitals of the penultimate shell. This is the definition of D block. Then, what is the definition of transition element? Actually, transition elements are those D block metals or D block elements which should contain incompletely filled d orbitals either in the ground state or in one of their stable oxidation states. So what is the definition of transition element? Those d block metals which contain incompletely filled d orbitals. Incompletely filled d orbitals in which condition, either in the ground state or in the one of the most stable oxidation states. So actually the controversy comes at two places. So So here you take the coinage metals, copper, silver, gold, and also take the zinc, cadmium, mercury. So this is 12th group. This is 11th group. Here the configurations 3D10 4s1, silver 4D10 5s1, gold 5D10 6s1. Now look at these configurations. 3D10 4s2, 4D10 5s2, 5D10 6s2. These two groups, if you compare, we consider the zinc group as non-transition elements, are not considered as transition elements. They are not considered as transition elements. Then this copper group, which we call coinage metals, actually their D sublevel is also filled. We should not treat them as transition elements, but in their stable oxidation states, they have incompletely filled orbitals, possess incompletely filled d orbitals in their oxidation states or in their ions. That's why treated as transition elements. Suppose I give 3 element is a set and ask which set does not represent transition elements. Your answer is zinc, cadmium, mercury. Copper, silver, gold are treated as transition elements because in their stable oxidation states, because just now we discussed cupric ion, Cu2 plus. Cu2 plus has 3D9 configuration. It has incompletely filled d orbitals. Like that, gold exhibits Au plus 3, auric chloride. Silver also in some compounds exhibits a different oxidation state. So this is one more point you should clearly understand. Transition elements are those elements which should contain either incompletely filled d orbitals, either in the normal state called ground state, or in one of the stable oxidation states, or in their ions. But if you look at the oxidation states of all other 40 elements, it is not possible for us, and also you don't get any questions in the examination. But you have 1 point, ruthenium and rhodium. they form compounds called ruthenium tetroxide, rhodium tetroxide, in which plus 8 is there. The highest oxidation state in the entire periodic table is plus 8. The highest oxidation state in the periodic table is plus 8, shown by two D block elements, ruthenium and rhodium, in their tetroxides, and also one P block element, xenon, in xenon tetroxide, also it is plus 8. So in the entire syllabus, you have plus 8 state in only 3 compounds. All these 3 are tetroxides. Ruthenium tetroxide, rhodium tetroxide, xenon tetroxide. This is a P block element. These 2 are D block elements. Here one important point is there. Generally, fluorine brings highest oxidation state. Whenever fluorine combines with others, it will bring highest oxidation state. For example, sulfur hexafluoride, plus 6. Iodine heptafluoride, plus 7. So generally, which element in the periodic table brings the highest oxidation state? Your obvious answer is fluorine. But in D block, fluorine won't bring the highest oxidation state. Oxygen brings the highest oxidation state, though it is less electronegative than fluorine. The reason is, in D block, when oxygen combines with the D block metals and form oxides, it forms P pi D pi multiple bonding, which is the root cause for their stability. So write that point. In D block metals, the highest oxidation state comes with oxygen. But not with fluorine. Because of the formation of P pi D pi multiple bonding. Because of the formation of P pi D pi multiple bonding. The next one, if you look at color, yesterday we discussed about some aspects of color, like titanium plus 3 in aqueous medium, cobalt 3 plus, dark blue, of course in aqueous medium, Mn2 plus aqueous, pale pink, Cu2 plus aqueous, blue or bluish green, so like this, the metal ions of the D block, either in the form of salts or in aqueous solutions, they are colored. The color is due to the presence of unpaired d electrons. Yesterday we discussed already. These unpaired d electrons absorb a particular wavelength of light from the visible region, from VGR. A particular wavelength of light is absorbed by whom? The unpaired d electrons, and they jump into another d orbital of higher energy, which we call it dd transition. So because of that dd transition, because of the absorption of a particular wavelength of light from the visible region, they exhibit color. Of course, some ions are not at all colored. Scandium 3 plus, aqueous, Zn 2 plus, cadmium 2 plus, mercury 2 plus, Ag plus, Au plus, Ti4 plus. All these are colorless. In an aqueous medium. Reason, due to the absence of unpaired d electrons. There are no unpaired d electrons. No unpaired d electrons. So this is all about color. Next one. Molecular or addition compounds. These molecular or addition compounds are divided into two types. They are double salts and complex salts. So as the name suggests, they are simply formed by addition, by adding. By adding two saturated solutions and on heating and cooling, new crystals are developed just by addition. That's why they are called addition compounds or molecular compounds, because they are combining at a molecular level. I'll give an example. If you take KCl aqueous solution in saturated condition and combine with magnesium chloride saturated aqueous solution, these two solutions are boiled and cooled. First you have to heat, second you have to cool. Two things you have to do. On cooling this combined solution after heating, you will find new crystals are being separated. If you put the test tube in a centrifugal machine and rotate, a new crystals are separated. These new crystals are KCl, MgCl2, 6H2O. It is called cornellite. And this is an example of double salt. Now if you take the second example, take ferrous sulfate, saturated aqueous solution. Next, ammonium sulfate, again boiling and cooling, you will get ferrous ammonium sulfate, FeSO4, NH4 twice SO4, 6H2. This ferrous ammonium sulfate is called Morse salt. Morse salt. If you go to the third one, I am taking potassium sulfate, to which I am adding aluminum sulfate. So you will get K2SO4 dot Al2SO4 thrice, 24H2. This is called potash alum. Which is also called common alum. Potash alum or common alum. So all these are double salts. So you can define double salt as a addition compound which is formed by mixing two saturated solutions, heating and cooling you will get. But one characteristic property of double salts, when dissolved in water, they completely ionize and lose their properties. So double salts can only exist in solid state or crystalline state. But when you dissolve them in water, suppose I dissolved KCl in water, carnallite I dissolved in water, it breaks into K plus, Cl minus, Mg2 plus, again 2Cl minus plus 6H2. It completely breaks. But in solid state, it exists. In water, it does not exist. So double salts only exist in solid state or crystalline state. But when dissolved in water, they completely break into component ions. Suppose if you dissolve more salt in water, it breaks into ferrous ions plus ammonium ions plus 2 sulfate ions. So more salt when dissolved in water break into how many component ions? Ferrous ions, ammonium ions and sulfate ions. Then you may ask me, how do you know it? You dissolve more salt in water. Will ferrous ion say hello to you? Yes, I am ferrous. Like attendance. Sulfate says, yes, I am there. like ammonium S, it says I am there. How do you know that? Each ion, by qualitative analysis, you can identify them. How do you identify ferrous ion? If you add any ferric compound, you will get ferric ferrocyanide, Prussian blue. What is the common test for ferrous? If ferrous ion is present in solution, add some ferric compound. This ferric compound and ferrous react together, form a complex, ferric ferro complex. So that is Prussian blue or deep blue. Now sir, I want to do a simple test. You add some sodium hydroxide or any base you add OH, you will get a dull green precipitate of ferrous hydroxide. Ferrous gives dull green. Then you may ask me how to identify the presence of ammonium ions. The best reagent to identify ammonium ions is Nessler's reagent. By which reagent you identify ammonium ions? Nessler's. So Nessler's reagent is K2HgI4 plus KOH. This mixture is called Nessler's reagent. Now this reagent react with ammonium cation and give chocolate brown precipitate. Chocolate brown precipitate called iodide of Melan's base. Iodide of Melan's base, OHgI HgNH2. That is the chocolate brown precipitate. Then you may ask me, if you go to the previous slide, how to identify ferrous over, ammonium is over, how to identify sulfate ion? Yes, anyone? Sulfate ions are best identified by any barium compound. Any barium compound like barium chloride. Immediately you will get barium sulfate, a white precipitate. So what is the best ion to recognize or to confirm that there is sulfate? Add any barium compound. Immediately you will get a white precipitate of barium sulfate, which is insoluble in concentrated HCl. So now you came to know that double salts are three examples or 4 examples are given here. So double salts are molecular or addition compounds which only exist in solid state, but when dissolved they completely dissociate in water. So giving test for the individual ions. Now then what about the second part here? Complex salts. These are also comes under same heading, molecular or addition compounds. So we are coming to the complex salts. complex salts. Take for example, ferrous cyanide, aqueous, add KCN aqueous, what these two are saturated solutions. Again we heat and cool. Immediately you'll get a new kind of crystals, K4FeCl6, potassium ferrocyanide. But this potassium ferrocyanide formed, when it dissolves in water, it won't completely break into component ions, but only it gives 4 potassium ions plus 1 This is the basic difference between a double salt and a complex salt. If it is a double salt, it will break into potassium ions, ferrous ions and cyanide ions. But it is a complex salt, it is breaking into only 2 parts. One complex ion in the bracket, one different ions outside the bracket. So complex salts do not completely ionize in water, whereas double salts completely ionize. I'll give another example. If you take cupric sulfate, aqueous solution, plus ammonia liquid, you will get a deep blue color complex, CuNH3 4 times, SO4. Write 4NH3 here. Now again you dissolve this complex in water. It's a deep blue color complex. Already copper sulfate is blue. This blue becomes deep blue. Blue becomes deep blue. That also we discuss in crystal field theory. Why the blue become deep blue here? You have to wait up to that. But this complex is dissolved in water. Only the outside sulfate will become one ion. The entire square bracket, 2 minus means 2 plus the other ion. The other ion is CuNH3 4 times 2 plus. This is called complex ion. Or this is also called coordination, complex ion, which do not or which exist in both solid state and in aqueous medium. Aqueous medium. So complex ions are present in both solid state and also in aqueous medium. They do not further ionize. Do not further ionize. We'll give one more example for complex salt. AgCl is a white precipitate. It is treated with ammonia liquid. When silver chloride precipitate is treated with ammonia liquid, you get a soluble compound, AgNH3 twice Cl. Write 2NH3 here. It is soluble. Any one doctor in this class, we already discussed this in P block, AGBR, present on photographic films, when treated with hypo, hypo is used as a fixing agent in photography. Under that heading we discussed, and you all marked it as important. Since it is important, you might have all of you studied well. Without referring the back pages, can anyone recall it? What is the complex formed here? So Na3 Ag S2O3 twice, sodium argento thiosulfate, a complex, soluble complex. So in this process, what we are doing, what are the silver bromide present on the photographic films is totally removed by forming a soluble complex. So what is the name of that complex? Sodium argento thiosulfate. IUPAC name? IUPAC name? Because it's an anionic complex, you have to start with metal first. Sodium dithiosulfato argentate 1. Sodium, you have to start with the sodium. Dithiosulfato. Sodium dithiosulfato argentate 1. What is the complex present in our bone marrow which produce erythrocytes or RBC? Vitamin B12. It is a cobalt complex which we call methylcobalamin. So vitamin B12 present in the bone marrow is responsible for producing erythrocytes or RBC. What is the complex responsible for carrying oxygen from your lungs to the entire body? Hemoglobin. So hemoglobin is a natural complex present in our human body. It is called ferroporphyrin complex. What is hemoglobin? Ferroporphyrin complex, where iron is in +2 state. What is the complex responsible for the photosynthesis process in which the green plants, which we call autotrophs, which manufacture their own food? The answer is chlorophyll. But there are many complexes. For example, COEDTA complex. COEDTA complex I put a minus. You know, EDTA carries how many negative charges? Yes, EDTA carries 4 units of negative charge because 4 acetate ions are there. This is EDTA. Each nitrogen carries 2 acetate ions. This is ethylene diamine tetraacetate. This part is ethylene. Ethylene is CH2 double bond CH2. This is diamine, imino part. Tetraacetate, total 4 acetate ions. So EDTA is a very important complex used by the doctors to recover or to remove the poison from the digestive system. If anybody accidentally or wantonly consumes any poisonous product, the doctor has to remove that poison from the stomach. Then they will give EDTA orally. This go and combine with the poison and form a complex. Later this complex, doctors give emetics. Emetics means vomiting agents, which create vomitings. So through vomitings, the person will totally expel out the poison which he consumed in the form of a complex. That complex is formed by EDTA. So EDTA is a medical application. Of course, EDTA is also used to study the extent of hardness in water. For 2 purposes we use. Now, one more important property after complex for size. Number 2, high charge density. Charge per unit area. Presence of vacant orbitals. So because of these 3 reasons, the D block metals generally form complexes. These complexes were first identified by Werner. That's why these are called Werner complexes. These complexes are also called coordination compounds. So coordination compounds, Werner complexes or complex compounds or complex salts, all these 4 are same. What are the 4 different names? Werner complexes, complex compounds, coordination compounds, or complex salts. All 4 are synonymously can use. magnetic property. So most of the d block metal ions d block metal ions having unpaired d electrons exhibit paramagnetic property. So how do you know that they are paramagnetic? The answer is very simple. When these compounds, or when those compounds which when placed in magnetic field, if the intensity of the magnetic field increases, then we call that substance as paramagnetic. When these compounds are placed in magnetic field, the intensity of magnetic field increases. The intensity of the magnetic field increases. Intensity of magnetic field decreases, then we call it as diamagnetic, due to paired d electrons or due to paired electrons. Repelled by the magnetic field. Intensity of magnetic field increases to many times. Due to similar spins of all the unpaired electrons of all the atoms iron, cobalt, nickel, scandium 3 plus, titanium 4 plus, Zn 2 plus, cadmium 2 plus, mercury 2 plus, copper plus, Ag plus, Au plus. So these are all diamagnetic. Nickel plus 2, manganese 2 plus, chromium 2 plus, cobalt 2 plus, Cu2 plus. So all these are para. So magnetic property exhibited by d block metal ions is of three types: paramagnetic, diamagnetic, and ferromagnetic. You know, paramagnetic substances are weakly attracted towards magnetic field, and diamagnetic substances are repelled by the magnetic field. These are strongly attracted towards magnetic field. Ferromagnetic. Here one more point. This is expressed in terms of magnetic momentum. Expressed in terms of magnetic momentum. So magnetic momentum mu is equal to root of n into n plus 2 Bohr magnetons. Here we also write mu spin only. Mu spin only. So write that point. In case of in case of 3D series, in case of 3D series, due to the spin of unpaired electrons, the magnetic momentum arises and the orbital motion does not contribute does not contribute to the net magnetic momentum. Actually, there are two types of movement for the electron. It spins around its own axis. Charged particle spinning around its own axis is the main cause for magnetic behavior. So electron not only spins but moves around the nucleus. That is called orbital motion. So two types of motion for the electron contributes to the magnetic property. But in 3D series, what they have found, the magnetic momentum is mainly due to spinning of the electron, but not the orbital motion or revolution around the nucleus. But in case of 3D and in case of 4D and 5D series, the spin-only magnetic momentum is not the correct value we are getting. We had to add two factors. One is magnetic property due to spin, the other is magnetic property due to orbital motion. So write that point, next point. In 4D, 5D and 6D series, in 4D, 5D and 6D series, the magnetic momentum is not due to spin alone.
So
Spin alone, ALONE, but also due to orbital motion of the electron. So see that formula mu is equal to root of n into n plus 2, where n is what here? N number of unpaired electrons. If you use that formula and determine the magnetic momentum value for the elements of 3D series, you will get some values, and those values are matched with the experimental values. This is the theoretical formula to know the magnetic momentum. But later the scientists have developed the practical way of determining the magnetic momentum. And in 3D series, this formula exactly matches the mu values which are determined practically. But in 4D and 5D series, the values obtained by this formula are somewhat less than the actual values. Then the conclusion is, so in other D block series, the magnetic momentum is not alone due to spin, but also due to orbital motion. So this is what we are going to sum up the magnetic properties. Next one is formation of alloys.
So what's magnetic momentum? Magnetic momentum.
Magnetic momentum is a factor to know the extent of magnetic property, paramagnetic property. It is one factor that quantifies how much magnetic property does a substance possess. It is a parameter. So magnetic momentum is a parameter. What that parameter indicates? How much magnetic property does a substance possess? Like, you may ask a similar question: what is dipole moment? Mu. dipole moment mu in chemical bond. It is also a parameter to determine how much polarity is there in a molecule. So this moment term in chemistry we are using at two places. One is dipole moment, another is magnetic moment. What does dipole moment reveals or suggests you? How much polarity is present in a molecule. But dipole moment, we define it as a product of charge and distance between the poles. So dipole moment mu is equal to E into D. But magnetic momentum, we are not defining. We are defining in terms of a formula.
So magnetic momentum, not moment.
Not moment. Magnetic momentum. Dipole moment. Similar terms. It is blinking red light. Oh, people are running fast. Okay, take the break now. So after this magnetic property, alloy formation, so the reason for why these metals, D block metals, easily form alloys. For example, nichrome. Nichrome is an alloy. Nickel, iron, chromium. When these three metals nickel, iron, chromium, if they are melted together, you will get nichrome in alloy. Nichrome alloy is used in electrical resistant wires. Like that, steel is an alloy. Steel is an alloy of iron, actually our ancestors used to tell, whenever you are going to get a sneezing and you should not stop it, thinking that what others will think, and you stop the pressure. It comes with a force. Suddenly people generally worried about others and they stop the intensity, reduce the intensity with which it is coming out. That causes the entire stomach region. The muscles are weak, soft muscles. So whenever people stop this sneezing with force when it is coming, the soft muscle in the stomach region, inside it gets ruptured. The muscle breaks. Because very soft muscle, weightlifters, suddenly if you lift a weight, inside the muscle ruptures. Behind the muscle, the digestive system will be there. So when the muscle ruptures, this digestive tract will protrude through the muscle, the fissured muscle, and a projection will come and appears as a projection on your stomach. Rupture is not outside, inside the muscle. This is called hernia. It may be umbilical hernia or any stomach region, multiple hernias. So hernia, there is no treatment. You have to go for a surgical operation. The surgeon will again put this protruded digestive system back and put a mesh. Earlier mesh system is not there. Now alloy meshes are there. That alloy is compatible for the human body. They put a mesh and do surgery. Again after surgery, if they do the same, at other place again, the muscle ruptures, the digestive system protrudes. So that is called hernias, multiple hernias, single hernias. It can cause to both male and female, anyone. Hernia is not a disease or a disorder for anyone. It is due to accidental pressure caused on the stomach muscles. Some people are having born umbilical hernia because umbilical cord, when they cut from the mother, generally the protrusion go inside when the child grows. In some cases, the protrusion will be there, visible protrusion in the umbilical region. Then see the wisdom of the ancient people. They used to put a rupee coin or any coin, press that protrusion and tie with a cloth. Because the child is just growing. Due to the pressure, because you press with a coin and tied with a cloth, it automatically goes inside without surgery and heals. So our ancient Indians used to do that. So this is what the bad impact of stopping the sneezings from your stomach becomes a great force. So steel is an alloy of iron, carbon plus nickel. If iron, carbon, nickel, it is called nickel steel. iron carbon plus chromium, chrome steel, iron carbon plus tungsten, tungsten steel. Steel essentially contains iron plus carbon plus other metal combination. Suppose iron, carbon, manganese, we call it as manganese steel. For example, this building, the strength of this building comes on this pillar, the vertical pillar and horizontal pillar. Like that, 1, 2, 3, 4, 5, 6 pillars are there for this building. You see the vertical pillars and the horizontal pillars. These pillars are called RCC structures, reinforced concrete. In RCC, what they use? Cement, chips, sand, water, they mix and put a steel frame first. The frame is filled with this RCC material. Then it becomes solidified and sets a strong object. So in RCC structures, steel is used, not iron rods. If you break this, look like iron rods, but they are steel actually. So why steel is used in RCC? A standard physics question in your heat chapter. Because the coefficient of linear expansion, alpha of steel and concrete is same. Alpha value of steel inside steel rods and concrete, both are same. So both expand to a similar ratio. That's why the pillar won't break or easily collapse. No sir, I have gold, too much gold, I use gold rods to construct my house. You may have satisfied that you use gold rods for constructing your house, but it won't give structural stability. Any nominal earthquakes, last week we faced an earthquake in Hyderabad. Not last week, 4 days back. Entire Andhra and Telangana both, including some part of Maharashtra, we have experienced mild tremors in the morning hours, around 7 to 7:30 in between. Mild, 30 seconds it lost. So actually all the buildings are anti-earthquake buildings. Means this type of pillars are there anti-earthquake. Because the building strength is based on this pillar. Pillars are deeply earthed also. Below the earth layers also it is connected horizontally, vertically. It is a framed structure. So the first precaution when earthquake comes, you have to hide under a table. That is the first precaution. So you have to see a table in your house and hide inside it. Because any collapse, first break your table, then only it comes to you. And you should not use lift. Elevators are not used. Only you have to use staircase only. There are some precautions. But anyhow, at that point of time, out of panic, we commit many mistakes. We don't know whether we are hiding there or exactly standing near the wall. If the wall collapses, we will also under the wall. So walls are easily collapsible walls. Because they are just a periodical arrangement of bricks only. Between brick and brick there is mortar. So brick and mortar structures. So the entire building, if it is shaken, walls only collapse. Pillars won't collapse. So to avoid that wall collapse on you, you are advised to hide under a table or run out of the house if it is possible. So different steels are there. Different steels. So actually alloy is Li is a solid solution. Li is a solid solution. A homogeneous mixture of two or more metals. What is the definition of an alloy? It is a homogeneous mixture of two or more metals, which may contain a non-metal also. Because steel contains a non-metal carbon. So sometimes alloys contain some non-metal also, but essentially it is a homogeneous mixture. Homogeneous mixtures are called solutions. They are in the solid state solutions. For example, ornamental gold. Suppose this ring. This ring is not pure gold. It is an alloy of gold plus cadmium. They are calling it cadmium gold. Or gold plus copper, gold plus silver. Generally the goldsmith mixes different metals to gold, pure gold. Pure gold is 24 carat. This is alloyed gold, it is 22 carat. It is a mixture of gold plus, I mentioned three metals, copper or silver or cadmium. So then only the gold will get flexibility to bend to the desired shape, because ornaments require many designs. Pure gold won't give that many designs. So pure gold ornaments won't be there. If you are purchasing a gold ornament, it is 22 carat gold. If you are purchasing diamond jewelry, it is only 18 carat. Further gold they decrease, because diamonds are very hard materials. If the gold percentage is more, they cut the gold. So ornament gold, the diamonds which are studded in pure gold, they will come out. The entire chain will break, because diamonds are very hard materials. So to keep the diamonds in your ornament, what they will do? They decrease the gold percentage, increase other metals, then they can keep the diamonds together. So all diamond jewelry is having less percentage of gold, take it for granted. They will tell you it is not pure 22 carat also, maybe 18 or 16 depending on, if more diamonds are studded, even less percentage of gold. So gold is also, ornamental gold or jewelry quality gold is also an alloy. Sometimes gold and mercury are mixed, which we call gold amalgam, used for filling the cavities of the teeth. Dentists. The Indian dentists are using two amalgams, gold amalgam and silver amalgam, for filling the cavities of the teeth, root canal treatment. So by removing all the original pulp present in your teeth, they make total free from living tissue, and the gap is filled with any filling material. The filling material they generally use gatta parcha. What is gatta parcha? Polymer of 2-methyl-1,3-butadiene. Polymer of 2-methyl-1,3-butadiene called isoprene. We discussed already. 2-methyl-1,3-butadiene, which is called isoprene. This is isoprene. This isoprene polymerize to give polyisoprene. This polyisoprene is like a rubberized material. It looks like natural rubber, but artificial rubber. Natural rubber comes from the latex from the rubber plants, rubber plantation. If you go to Kerala state, I don't know in your state, in you have here also, yes, okay, very good. Garo Hills, he is telling. So there, every tree is attached with a bucket, the groove. Latex will come into the bucket, and they what they do, they coagulate this latex and make rubber materials. Later that is processed and made in different varieties. That is natural rubber, but artificial rubber is polyisoprene. I think in Garo Hills, Eri silk, ERI. It is the top product in Meghalaya. Eri silk. It is called non-violent silk. It is also called ahimsa silk, because the silkworms usually they fed on mulberry leaves. But here in Meghalaya, the silkworms are fed on resinous communis leaves, castor oil plants. So here the silkworms eat that, not mulberry leaves, resinous leaves, and they build a cocoon. Actually, cocoons are usually boiled and kill the inside the worm, silkworm. It will be killed actually in normal silk. But in Meghalaya, what they do, they open the cocoon and so that the worm escapes. So no killing of these worms. That's why it is called a non-violent ahimsa silk. It is called Eri silk, ERI. This Eri silk and Eri silk mufflers, stoles. Stoles means maybe shawls type, I don't know. So stoles, shawls, mufflers in Meghalaya are made with Eri silk, which is famous and costly also. So that also you should know about your state. Okay. So that polyisoprene, usually called as gatta parcha. Dentist called GP. Why I said Indian dentists are using this gold amalgam and silver amalgam for filling the teeth, AU plus HG. If the alloy contains mercury as one of the component, we call it as amalgam. But mercury is poisonous for the human body. Thus in the entire West, Europe and other countries, all countries, almost around 30 years back or 40 years back, they banned this dental amalgam. Dental amalgam is gold amalgam, silver amalgam. So both were banned because they think that the filling of the cavity by this material, some mercury during their lifetime, it goes inside and causes many dangerous diseases, mercury poisoning. You have studied mercury poisoning in your Minomata disease in Japan. Minomata Islands of Japan, where the people ate one kind of fish and all people died. The post-mortem report reveals that they are poisoned by mercury. Immediately they checked what these people ate in the previous night. They said in this restaurant they ate. In the restaurant what they ate, they checked the order. They ate one kind of fish. Immediately they seized the remaining samples of the fish and identified those fish come from a particular lake, and that lake was poisoned by mercury. So mercury wastage pollutants entered into the lake where the fish consumed that mercury. That fish they ate, and finally all of them died. It is a world famous disease called Minomata disease. It's a general knowledge question also. Only in the Minomata Islands of Japan. Because Japanese eating habits are somewhat unique. Though they live long, if you go to a restaurant and ask fish, they will cut a slice and put in, just dip in salt water and give it to you. No cooking, nothing. Horrible way of eating. So even the fish smell also comes. So our Indian cooking is entirely different. Actually, Indian cooking is a high temperature cooking, our cookings. Even if it contain virus, gyrus, and all, everything will collapse here. Because when bird flu hits the Hong Kong and Hong Kong mainly, Indians when they are worried, the veterinary doctors say no. Even the bird flu, chicken if Indians eat, nothing will happen. Because it is high temperature cooking. The virus will destroy, even the bird is having that virus. So you need not worry. Here people eat pork. Pork with tinea solium, there is a problem. Tinea solium. Pork is the secondary host. So when pork is having some dots, it is called measles pork. Pork having dots, the dots represent the head of the tinea tapeworm. So even in the high boiling conditions also it survives, the small head region. When human beings eat that pork, it go and attach to your intestine, that small head region, and slowly the remaining tape develops. A big tapeworm will be there in your body. It is called teniasis, helminthes. In this teniasis, it acts like a blotting paper. Whatever the food you eat, it absorbs. Whatever the food you eat, it absorbs. Ultimately, food is not going to your body. It is taken by tinea. So ultimately, the person becomes lean and further lean. He is naturally lean, don't think. So doctors test the stool, excretory part, and in that this developed tapeworm loses its tape part by part. They are called gravid proglatids. They are visible in the stool, that is excretory product. From that they will confirm that this person is having teniasis. So that is only due to not this pork. The pork which you are eating is different. This is grown in farms. They are fed with tuberous roots and all these starch material the animals eat. But they are raw pigs, black. They eat all waste. So they develop this teniasis. That is again transferred to the human beings. So that is different. This pork is different. So you need not worry, because mushrooms Gautam Buddha ate mushrooms and died in the last. That doesn't mean mushrooms we die. Colored mushrooms are dangerous. You know that? You should not eat colored mushrooms. Mushrooms should be pure white. Colored mushrooms are highly poisonous. Maybe Lord Buddha ate that at that time, Buddhistic time before Christ. Before Christ. Buddha lives before Christ. So he don't know about colored and non-colored, uncolored. So somebody he ate and Buddha died because of mushrooms. This is what the story tells. Okay. So after alloy formation, interstitial compounds which are non-stoichiometric. So what are these interstitial compounds? So whenever the D block metal atoms are packed in a proper order, whenever atoms are packed in a proper order, we call this as crystal lattice or space lattice. This is crystal lattice. Or space lattice. These gaps are called voids or interstices. Voids or interstices. Here also you can see one void, here also one void. So whenever a D block metal is heated with a non-metal, the non-metal atoms occupy these gaps. Suppose if it is carbon, carbon atoms will occupy here. So if the interstices or voids are occupied by carbon atoms, you will get an interstitial carbide. If the interstices or voids are occupied by nitrogen, you will get interstitial nitrides, interstitial hydrides. So many interstitial compounds. What are interstitial compounds? Those compounds which are formed by occupying of or by the occupation of non-metal atoms in the gaps or voids or interstitial spaces of the D block metal. Now, the question is, how many gaps are filled with non-metal atoms? We don't know. So the composition of the interstitial carbide is different because how many gaps or voids are filled with carbon atoms, we don't know. That's why there is no fixed composition between the combining elements. And the interstitial compounds do not obey normal valency rules. That's why their formulas are also different type. Suppose Fe O 0.71, they give formula like this. Or they give the formula like this. FeO, here they give 0.93. Not one Fe, one O. Per 0.93 iron atoms, one oxygen is there. So formulas are different. Fractional formulae, different formulae will be there. So they are called interstitial compounds which do not obey normal valency rules, do not follow normal valency rules. For example, you take second group, beryllium carbide. Oh, this is over. Beryllium carbide. What is the formula of beryllium carbide? Be2C. What is the formula of beryllium carbide? Be2C. After beryllium, what is the next element in the same group? Magnesium. Magnesium carbide formula, this is Be2C. The next element formula, Mg2C3. Next calcium carbide formula, CaC2. Within second group, with carbon, the element, second group elements valence is fixed. How much it is? 2. So when second group elements formula is fixed, carbon valence is fixed, it should be Be4C2 or Be2C. It is obeying the normal valency rule. But after that, magnesium carbide, Mg valence is 2, carbon valence is 4. Again, what is the expected formula? Mg4C2 or Mg2C. But what formula we got? Mg2C3. Similarly, calcium carbide, you should get similar formula, but you are getting CaC2. So whenever the carbide formula is not obeying like normal valency rule, we call that carbide as interstitial carbide. Here write one more point. The extreme hardness of steel is due to the formation of an interstitial carbide called cementite. Fe4C. Fe4C. This is the reason for why steel is very hard. This is an interstitial carbide. Interstitial compounds possess more hardness but typically they behave like metals in their conductivity, but typically they possess the electrical conductivity like the metals. But they are physical compounds in which the non-metal atoms are trapped. The non-metal atoms are trapped in the voids or interstices of the crystal lattice of the metal, and they are trapped in the voids or interstices of the crystal lattice of the metal. Next, catalytic property. Catalytic property. D block metals or their compounds act as catalysts due to number one, large surface area, in the powdered state, or finely divided state. Number two, presence of free valencies. Presence of free valencies. So we'll see some examples how the D block metals act as catalysts. So now, process catalyst. Write Haber's process. So in Haber's process, we manufacture ammonia by combining nitrogen and hydrogen. Here iron is the catalyst. Number two, contact process. Here you can use platinum or vanadium pentoxide. Next, number three, hydrogenation of oils. Hydrogenation. Nation of oils. We use nickel catalyst. Number four, Ostwald's process. Platinum. Platinum is the catalyst. Sabatier-Senderens reaction. In Ostwald's process, what do you use? Platinum. What we manufacture? Nitric acid. Ostwald's process is meant for HNO3. Nitric acid. In hydrogenation of oils, what we make? Dalda or vanaspati. Vegetable oils are converted into vegetable fats. Ghee is an animal fat. So whether it is cow ghee or buffalo ghee, it is an animal fat. You have vegetable fat called dalda or vanaspati, where the vegetable oils are hydrogenated by passing hydrogen gas in the presence of nickel catalyst. It converts into a solid. That solid is called dalda. Sabatier-Senderens for what? Alkenes and ines. Alkynes. Enes and ines are converted into anes. That is Sabatier-Senderens. Now you have studied one more process. In the chlorine manufacture. In chlorine manufacture you have studied one is Nelson's process, the other is Deacon's process. Write that. Deacon's process. DEACON apostrophe S. Deacon's process. Catalyst is cuprous chloride, CuCl, or cupric chloride, CuCl2. Deacon's process is for the manufacture of chlorine. What the catalyst we use? Either cuprous chloride or cupric chloride, CuCl or CuCl2.
So what is the catalyst in the process page?
Which one? Sabatier-Senderens, same platinum or palladium or nickel. Three can be used. Nickel or platinum or palladium. Nickel or platinum or palladium. Okay. So what is the reason for the catalytic activity of the D block metals or their compounds? For example, you write in the process decomposition of potassium chlorate. I add one more. Decomposition of KClO3. Under the process, you write decomposition of KClO3, potassium chlorate. Under the catalyst heading, you write manganese dioxide, MnO2. Actually, catalytic action, you always know that it is highly specific. A catalyst in one process cannot act as a catalyst in other process. Like you can't unlock a lock with all available keys. A proper key can unlock a lock. That's why what we say catalytic action is always highly specific. With a particular lock, with a particular key only you can unlock it. No sir, I have 100 keys of different locks. One will fit into this and no. For unlocking a lock, you require a proper key. Similarly, for catalyzing a process, you require a proper catalyst. Our human body, the digestion process and many processes occurring in our body are highly catalytic activity properties. Suppose you ate food containing protein, starch, fat, fiber, many type of food, it goes into our stomach. So some part will be fats, some part will be carbohydrate, dietary fiber, protein, many are there. So how the body digests all of these? Every food material require a particular catalyst for digestion. For example, the gallbladder secretes the pancreatic juice. So that green color liquid comes from the gallbladder. Gallbladder connecting the liver and digestive system. Whenever you eat more fats, the liver sends that bile juice into the gallbladder. Gallbladder contracts and pump that bile juice into your digestive system. It digests all the fats. Sometimes gallbladder develops stones. So when gallbladder contracts, the bile juice cannot enter into that. And you will get severe stomachache. If that is go on repeating, doctor will identify it is due to stones in the gallbladder. They do a small surgical operation, remove the gallbladder and directly attach liver to your digestive system. It is called cholecystectomy. So the gastroenterologist will do it. So like that. So body also contain many catalytic actions for digestion of the food and do many biological processes. It's a complex complex chemical reactions are occurring in the human body at human body temperature. Human body temperature is very simple. The same catalyst, if it wants outside of the human body, it requires hundreds of degrees of centigrade. But the human body within 30-35 degrees, same reaction, same product, but due to catalyst, it occurs at body temperature. So this is very complex mechanism of catalytic actions in the human body. So there are two reasons for why these are acting as catalysts. One is due to the large surface area in the finely divided state. So generally in the chemical processes, we use catalyst not in the form of lumps, in the fine powder. This powder spreads, surface area increase. On the surface it will absorb the reacting molecules. The reacting molecules easily react on the surface of the catalyst and form the product. and the catalyst should be in a position to tell the product, your job is done, you escape from me. So it is all occurring on the surface. Adsorption of the reactants, react and form the product. Product should get out from the surface, which is called desorption. So adsorption, desorption, adsorption, desorption. It's a continuous process. Like that, catalyst acts. A small amount of catalyst is sufficient to carry out a big industrial process. No, sir, industry, we are using tons and tons of reactants. Shall we add tons and tons of catalyst? No. Then it is not called as a catalyst. So catalyst, a small amount should be able to bring the change. How a small amount can convert that many reacting molecules into products? That is very simple. It is adsorption and desorption. If the catalyst surface is held by all of the molecules, they say, no, we don't want to leave from the surface. We are reacted here. We are liking this catalyst. We want to hold it. Then it is no longer a catalyst. Every half an hour you have to change the catalyst. It is a headache business. So they choose, even in the motor bikes, nowadays for automobile industry, they are using catalytic converters. Your fuel burns in the carburetor. The waste gases come from the silencer. So the silencer tube is fitted with a sponge type, solid state, porous, spongy type catalytic converter. What it will do? It will absorb all the poisonous gases and convert them into non-poisonous and send them out. So that the global warming, other pollutions can be prevented by using catalytic converters. So this is catalytic activity of D block elements. So if you nutshell, if you sum up all the general characteristics of D block, we have studied the variable oxidation states, complex formation, color, magnetic property, interstitial compounds, catalytic activity, alloy formation. So all these comes under the general properties of D block elements. Next one, F block also shows similar properties. So once you study the properties of D block elements, you are already studying the properties of F block elements. Both D block and F block metals, they show variable oxidation state, they easily form alloys, they form interstitial compounds, they form complexes, they exhibit color, they exhibit three types of magnetic properties, para, dia, ferro. So I mentioned in ferromagnetism, the spin of all the unpaired electrons should be the same. The alignment, spin of electron is clockwise or anti-clockwise. If all these single electrons present in the substance have all of them a clockwise spin, all are projecting upwards, the alignment is similar, then the substance become ferromagnetic. So ferromagnetic substances should have a proper alignment or arrangement of the spins of all the unpaired electrons of all the atoms. That creates a magnetic domain. Because of magnetic domains, they are ferromagnetic. Iron, cobalt, nickel, I mentioned. Ferromagnetic substances are used to are used for making permanent magnets. So permanent magnets are made with ferromagnetic. But nowadays I don't know. Mostly scientific community are using the magnets made by neodymium in lanthanide series. Lanthanum, cerium, praseodymium, neodymium. The fourth element of lanthanide series. Lanthanum 57, cerium 58, praseodymium 59, neodymium 60, atomic number 60. that neodymium is used nowadays for making the permanent magnets, and which are also very strong magnets. So this is all about the general properties of D block. Now in the next class we start a block, and also in D block, write 2-3 points we ought to discuss, headings only. Discussion of the E naught values. Discussion of E naught values within bracket SRP, standard reduction potential. SRP values of M2 plus 2 electrons. M2 plus 2 electrons gives M. And also M3 plus 3 electrons gives rise to M. So addition of electrons is called reduction. So here what kind of ions we are taking? M2 plus ions and M3 plus ions. These two we have to discuss. M2 plus aqueous, 2 electrons gives M solid. Similarly, M3 plus aqueous, M solid. Actually, the E naught values we call standard reduction potentials. SRP values. If you look at the first transition series, titanium, vanadium, chromium, now some of you, any one of you should see the textbook and give the E naught values. From that we understand the E naught values. I did not write scandium 2 plus because scandium do not form 2 plus ion. So we started with Ta2 plus. I think it is minus 1.18. 1.63. Next, minus 9. Next,
minus 1.18. Minus 0.44. Minus 0.28. Minus 0.3 plus. Minus
0.25. Only copper will have plus. Minus 0.76. So actually, These reduction potential values are very much irregular. So in the first transition series, the standard reduction potential. Reduction means addition of electrons. For M2 plus ion in aqueous medium, if 2 electrons are added, you will get M solid. This is called reduction. When we call standard reduction potential, if we take the concentration as 1 molar, if we take the concentration of the ion as 1 molar, then the potential developed we call standard reduction potential. The first point you have to know that is the irregular variation of the SRP values of the SRP, standard reduction potential values, indicate that the sum of energy changes involving IE1, IE2, delta A H sublimation or atomization and delta hydration H show irregularity in values. So why these SRP values are irregular? So the answer is, so whenever a metal solid to convert into metal solid to metal gas, direct solid to gas, any change we call sublimation or enthalpy of atomization. That is I indicated delta A H. A means atomization. So here delta H is enthalpy of sublimation, or it is also called enthalpy of atomization. Is it exothermic or endothermic? When a solid has to convert into gas, means you have to provide extraordinary energy. First, a solid should be melted and convert into liquid. Liquid should be again converted into gas. So two changes are occurring inside, but only visibly we can see one change. Whenever a solid is to be converted into gas, it is a highly endothermic change. So it is having delta H positive. Delta H positive. So first energy change you require is solid to gas conversion. What is the second energy change? This M gas, you have to supply first ionization energy, IE1, so that it lose an electron and convert into a uni-positive gaseous ion. Now this M plus gaseous ion is supplied with IE2. Now you will get M2 plus gaseous ion plus electron. If you add these two changes, this and this cancel. So M gas IE1 plus IE2 IE1 plus IE2 gives M2 plus gas plus 2 electrons. So how many changes are over now? 1, 2, this is 3. Net change I wrote. Now the fourth change is this M2 plus gaseous ion in aqueous medium attracts N water molecules What is this fourth change called? Whenever a particular ion attracts water molecules or water molecules surround that particular ion, we call it as hydration. Here it is the energy involved is enthalpy of hydration. Here I mentioned. So the enthalpy of hydration is always exothermic. So here delta H is negative. Now to that M2 plus aqueous ion. Finally we got M2 plus aqueous ion. Aqueous means water molecules. We are adding 2 electrons to give M solid. So to obtain this ion, how many energy changes are involved? 4 energy changes. What is the first one? Enthalpy of sublimation or enthalpy of atomization. What is the second energy change? Second energy change is this one. Removing 1 electron from the M gaseous ion, gaseous atom. We are removing first electron. Later the third energy change is IE2. The fourth energy change is this gaseous ion is attracting N water molecules to form a hydrated ion. So the sum of these values given in your NCERT textbook, I think table number 8.4. Is it 8.4? Correct? Okay. In case of titanium, to form titanium 2 plus aqueous, to form this, what is the enthalpy of atomization? First column. 469. So 469 is delta AH plus what is IE1? 656. This is IE1. What is IE2? 1309. This is IE2. All these are endothermic. That's why we are giving positive signs. What is delta H hydration? Minus 1868. 66. Now if you do this, you will get some value. Anyone did? Add the 3 and subtract this. $568. So you'll get 568. And the E naught value is given. Minus 1.6. E naught values we already given. Minus 1.63 volt. Now if you look at the titanium, next one, vanadium. To give vanadium 2 plus, if you do all these values, you will get 684. The final value I already worked out. 684. And the E naught is minus 1.18 volts. Next, chromium. To chromium 2 plus. If you do that, you will get 718. 718, and the E naught value is minus 0.90 volts. Similarly, if you do Mn to Mn2 plus, if you do all the additions from the table, you will get the net energy 643. And again E naught is equal to minus 1.18 volts. After that you do iron to iron 2 plus. Later you can check. You are getting 743. And E naught is equal to minus 0.44 volts. Cobalt to cobalt 2 plus, we are getting the net energy change 750, and the E naught is